Hey guys, it's Jared with Midstate Engineering, and today we are going to be going over Fanuc's IRVision, more specifically the 2D vision setup. And we will be referencing the R30IB controllers. So let's go ahead and jump right into it. So I had to take a pre-recording video of a robot when I was out on the floor, when I was hooked up to a real live robot and I was setting it up because clearly I don't have a robot, I don't have our vision, and I don't have parts to test on. But I did when I made this video. So I apologize now if it seems like I'm all over the place, but as I'm going through the video, I'll pause it, start it, and stop it to explain things. So um, some of the prerequisites, right? You got to have your camera set up, whether it's power over Ethernet or it's the bayonet connectors, it has to be hooked up to the robot controller. Um, so really quickly, you want to have a cal grid. When you get IRVision, you want to have a cal grid that fits the most space of the field of view of the camera. So we usually use the 30 mm spacing. So those are the biggest cal grids that Fanuc gives us, and that gives you better accuracy. So what you don't see in this video is us lining it up. And so what we do is we go into IRVision, and let's see if I can actually do it. Let's see if I can just show it to you because I have a robot here, but but it's a virtual robot. I don't think I'm going to be able to do this, but up here where my cursor is, there's a crosshairs. And what you want to do is you want to get that crosshairs lined up perfectly to the origin, to the center of that cal grid. There's a little dot. You want to have it as perfect as possible. If it's not, that's okay. We actually just calibrated a robot last week and the crosshair wasn't lined up perfectly in the Y dimension. That's fine. As long as we had it lined up in the X axis and ended up working fairly well. So let's go back to the video and let's just start it. So I'm on the browser here. You can see I typed in, I already have the host com set up. I'm connected to the robot through the Ethernet switch. I typed in the robot's IP, and here is the IR vision screen. So we are going to do a 2D single view vision process, which is usually what you're going to be using. Here on the right hand side, it describes to you that look, you have a single camera, a single robot, and the camera is mounted to a fixture. It is not a robot mounted camera. So that's what we're going to be going over in this process. So because we're doing a positional stuff instead of just inspections like you would do in a single view inspection viz process, we are using positional data. So here I'm creating a 2D single vision process. But before we do this, we go into calibration, right? We got to have the robot calibrated. This is when you would have the cal grid right in front of the robot. Here on camera, you would select what camera you have, exposure time, and you would also, while you're looking at the camera, looking at the cal grid, trying to get a good picture, you're also adjusting the aperture and exposure of the focus of the lens, of the actual lens. We get these lenses that have two settings on it, on the physical lens where you can adjust the aperture, how much light comes in, and you can adjust the focus. And you can do that before you get the cal grid set up here. You have it lined in with the crosshairs, and then you want to um, get a really good focus. And typically, you would be able to see some of the lettering here. Now, in this picture, the contrast is washing out the image. Well, we're going to take care of that later down in the process. So calibration setup, application frame. This is our user frame that we taught. So, like I said, all over the place. I know, I apologize. I don't have a real life robot, so I can't go through these steps. But when you have your calibration set up, you want to get your cal grid set up. The origin matches the origin of the camera. It's perpendicular. It's perfectly perpendicular, perfect 90 degrees up. You want it to be perpendicular. Um, you don't want it to be shifted and yaw, pitch, or roll. You don't want any of that. You want it to be perfectly lined up. And when you're doing this, I made this mistake last week. When you teach the frame, call it calibration frame, use user frame 9. You want to use the 4-point method to teach your user frame. So before you even do your calibration, get the cal grid up there, line it up, and then come in here to set up frames, user frames, details, method, 4-point method. This is the most accurate. System origin is the center of the cal grid. That is the center dot of the cal grid. Your origin, as you know, with user frame, it's the bottom left. I guess depending on where your user frame is, but it would be the bottom left dot if X is this way, Y is this way, and Z is positive. Your origin is going to be the bottom left dot. The system origin is the very center. So I just did the 3-point method at first, and my VR offsets were not accurate at all. So get your user frame taught. And then in here, in your application frame, you can point it to that. And I think there's a couple steps after this where you will also point it to that user frame that you taught. Thus, that's why you have to have the user frame done beforehand. Again, here we are in the fixture position. We're looking at the cal grid frame. Override focal distance. So on the lens itself, there is a standoff distance you could override, but we do the focal distance because that is a known distance that we already know, because we know that the focal distance of the lens is a 12 millimeter lens. So we can put that in there. We know that instead of just measuring with a tape measure and saying this is the standoff distance, that's the other option here. Just use the focal distance. If you find that your cal grid is skewed a little bit, after you put in your focal distance, it's going to calculate your standoff distance. Ours was about 1,268 millimeters. I took a tape measure, I measured it, and that was pretty darn accurate. After it tells you your standoff distance, you come down here and click OK, and then you click Find First Plane. Now, this first and second plane is actually really cool if you have a robot mounted camera, but since this is fixture mounted, we're only doing first plane. But having 1 and 2 planes, that helps you. It almost turns a 2D camera almost into a little bit of 3D functionality. You get your degrees of freedom, like orientation, rotation, and I think there was another one called aspect, how much it moves in this dimension. That is a little bit of 3D functionality. And when it's a robot mounted camera and you use these 2 planes, you can really start to dial in some of those degrees of freedom. But when you do find your first plane, then you're going to put the field of view of that search window directly over your cal grid in real life. And then, so if your crosshairs on every single dot are skewed a little bit, after you do a find, they'll be dead on. It will find every single dot, and it will tell you which dot is every single dot. Here, there's the 4 dots in the middle. One is your origin. These 3 dots is telling you your X direction. So X positive is in this direction. Y positive is in that direction. And it will also say on the cal grid. So let's keep playing this video. Otherwise, this video is going to be 20 minutes long. In the calibration points, it's going to tell you every single point it found. So if it found a point that isn't on the calibration grid, you can go in there and delete it. Here it's telling you some of your distances here. Your standoff distance, this is a different. So ours was 731 millimeters for this application. Max lens distortion. You really want to see single digits on here. I had a max lens distortion. It was about 12 pixels and it still worked. It still worked, but your error values, you want to pay close attention to these. Your focal distance, you typically don't want to have I believe it is your scale to be less than, you want it to be less than 0.5. Okay, let's keep on chugging. So now your calibration is done. Calibration is done, and we are going to do our process. So I just took the class a month or so ago, and the steps go like this. You do your camera setup, which is your calibration. You're finding your camera. After that, once you find your camera, do your frame, and then circle back to calibration and finish calibration. After that is our processes. What are we doing? Are we going to do a 2D single view process? Are we going to do a single view inspection vision process that doesn't have any positional data offset? And then after that, we're going to go into teach pendant code. So here we're going to have some red dots. We're going to have some exclamation points here. You want to point it to the calibration that you made for that camera. Point it to that calibration. If it's calibration 1, if you have 2 cameras connected to the same robot, make sure you differentiate between the 2 different calibrations for that specific camera. Offset mode. Number to find, we're actually looking for 10 different parts. And here we're going to do a fixed frame offset. And then we're going to find the user frame that we taught as well. They have these nice informations boxes or comments that describe to you what each one is, and you can go into them and read them and see what the difference between a tool offset is versus a fixed frame offset. And then we're going to go find our user frame, that calibration grid user frame that we taught earlier. Still, we have a really washed out cal grid, but before I go into that, I'm going to set the search window for our tool. This is where the camera is going to be taking a picture at. This is what it's going to be working in. So the snap tool has a search window, and so does our GPM tool, which is our GPM, our geometric pattern match tool. That is the pattern that we're going to be looking for. Exposure time, bam, look at how that pops, right? Look at that contrast and difference. Now that's a really low exposure time, but we are going to want to display, instead of the entire image that the picture takes, we're going to want to display the snapped image, which is going to be important when we go into our GPM tool. There are other tools that you can add to this. Image filter tools, which is another way of saying an image enhancing tool. So if you have a really pesky part, you're really struggling to find it, you can use some of these image enhances to filter it in a way that might be easier for the GPM tool to find. Now, this image filter tool is a parent tool to the GPM tool. It's what we are going to be feeding into the GPM tool. So we're either going to use the snap tool for the locator tool, or we're going to use the image filter tool. You can't use both. I'll show you a little bit what that's like. I can't really remember for this application. Yeah, look at how that pops. Looks totally different. I don't think I end up using this, but it's there if you need it. I wanted to show you how that works. Excuse me. So this is where you choose that, your input image. You choose you're using your snap tool or your image filter tool. Now let's teach. This is the cool part, right? We're going to take our perfect part. We're going to take a picture of our perfect part. We're going to narrow it down into one part because that's what we're looking for. If I'm trying to look for a good example around here, if I wanted to pick this pencil, and this is where I'm going to pick it from, I'm going to take a picture of the entire image, right? Because I want to see this side, I want to see this side. That way I get a good center of origin, especially for rotation. It's not a very good example, but this is a really easy part because it's a circle. Last week we just did calipers and knuckles on your brake pads. So I'm going to zoom in. I zoomed into this. I want to get a really good picture of this. Make sure my edges aren't too big. I don't want any of this white space. I want to minimize as much of this white space as possible. I want the perfect image. Everything highlighted here are the details that it's finding. It's seeing the details on the outside and seeing the details in the inside. That's what we want to see. And we can filter those. We can use this training mask. And a really easy way to use that training mask, I'm trying to think of a good way that would show you this, is what I would do is I would mask the entire image. Let's see if I can show you. What I would actually do, let's see if I can show you. Here we go. I would mask the entire image and then I would come through and erase parts of the image that I would like to see. So if I want to see this image here, if I want to only see this circle here, I don't want to see all these extra details here in the center. Maybe I don't want to see the center. I want to see the outsides of these edges only. This would be a good way that you can mask that. For example, okay, back to the video. And I apologize, you guys, for being patient with me. This is really hard to do with a pre-recording. So this is an emphasis area, which gives you a separate score from your overall score, which lately I haven't been using this because yeah, your emphasis, it may be finding the image, what you're emphasizing, it may be finding those details, but what about the rest of the details? And if you emphasize as many, if I emphasize all these details, it would tell me that my emphasis area is too large. So it's something I use sometimes. You can compare it in an execution tool. You can compare it instead of looking at the overall score of original your original picture, your original GPM train tool. You could look and compare it to the emphasis area score. It's the EA score. And if it's 100, and if it's greater than 80% of the EA score, it passes. But usually I just use the entire score threshold right here. So I'm going to save it. I'm going to snap and find. And now it's going to show me pictures of everything else that looked like that original picture that I took. Now it's not finding these other ones, and I think it's because they're all touching and it's not getting that whole circle. It's not seeing those details in these other pictures. So you can see the different scores here that it's passing. Its overall score compared to the one that we taught. 97 is the highest, 88 is the lowest, and then our EA score. Look at that. It's all 100%, right? All the way scroll down on here, which I'm going to show you. Scroll down on here is a show almost find. Use that. You can use that as a tool to see if you are finding things, you are potentially almost passing things that should not be even nowhere near close to passing. You can use this almost found as a tool to help you dial in your variables. Let's get back to the video. Here's that training mask I was telling you about. I'm gonna edit out the circle on the inside. I only want to see the circle on the outside. There is our score threshold. That's where we're getting that 89%, 88%. If I wanted those 88% to fail, I would crank this up to 90. I could say it needs to be a 90 or above to pass. And here we can mess with some of the contrast of the GPM tool. Elasticity, that is how much can it change in shape and size from the original picture that we taught? How much can it move around? How much can it differ in size? Area overlap, I usually typically only allow about, usually not 75%. I usually only allow about 10%, but it also depends on your part. So let's go back there a little bit because there I was just looking at our degrees of freedom. So earlier when we snapped and found pictures, you could see them how they were skewed a little bit in rotation. The robot's going to come down and see that and it's going to rotate because the picture thinks that it's rotated, 5 to 60 degrees. I do not want that robot to rotate. I mean, that can get pretty unpredictable pretty fast. Excuse me. So what I do is I actually get rid of this orientation. I say that it can only be perfectly square. And what you're going to see is that rotation. You're going to see that rotation go away in those images. We'll do a snap and find. I'll save it, snap and find, always save. There's that almost found feature I was telling you guys about. Here, I'm going to add a histogram tool. I believe what I was trying to do with this is to be able to tell that a part is laying inside or on top of each other. I should be able to see that the center of this circle is perfectly white. I should be able to see that. If I find a circle, but the inside of it's not white, then I'm assuming that there's a part laying on top of each other. That's the region that we're going to be searching for here. We did this project months ago. So I'm trying to refresh my memory on this application. But we use IRVision all the time. We use IRVision a lot, a lot, a lot. And it is very powerful. What you think that you would need Cognex for, or a powerful camera like Cognex or Keyence, you could easily do with Fanuc Vision. So much cheaper. So 255 being completely white, 0 being completely black. So when I taught this region, I masked out the center. I'm looking for that nice white area in the inside of these circles, and these are passing. When I did a snap and find, it's finding them, which is awesome. Now it's time to do a conditional execution tool. Yeah, it's great that it passed, but what are we going to do with that? This conditional execution tool allows us to do compares. So yeah, it passed and failed, but the robot is not doing anything with it. The software is not doing anything with that until we make a conditional execution tool. So you can see that the histogram tool is a child tool of the GPM tool, as well as the conditional execution tool. I am saying that the value of the histogram tool within range of its score, its value has to be less than the constant of 80. Okay. So those were all of the bells and whistles of IRVision, but getting down to the heart of it, the conditional offset, the calculation tool. This is where you get your offset. This is where you get your positions from. Now, the part Z height, it is asking you the height of the part from the calibration grid. So if the calibration grid was taught here, the parts on top of here or below it, if it was below it, it would have a negative value, right? If it's above it, it's going to have a positive value. So if the calibration grid was this far away, but the part rests up here, you're going to say that that part Z height is that distance. And I believe it has, if you hit the I, it'll tell you. Yeah, here it is. Yep, the workpiece or the table being the calibration grid. They don't really describe that very well. So that was a good demonstration there. I hit set before I did a snap and find. You have to do a snap and find and then hit set. When you do this, and I think I may hit on this a little bit, but when you do this, okay, it tells you in here that a trick to do this is to teach the robot position first. Go in there, teach the robot position, teach the PR, the point, whatever position you're using. We use PRs because you can manipulate those globally. We'll come in, we'll teach that point, and then without moving this workpiece, without moving it, I will come up and out, make sure the robot's clear of the camera, and without moving the workpiece, this is very important. You come in here and hit set reference position. That's your 0. A good way to test this to make sure your calibration's good, your GPM locator tool is good, to make sure everything is good. When you come in and you take a picture in the teach pendant code, when you come in here and take a picture in the teach pendant code, you do a run find of this routine being education. So when you go in here in choice, sorry, it's actually not going to let me. Okay, here it is. Locate rotor. That's the vision routine that was inside of this teach pendant. This is a different robot. But here you would find this routine called education. That would be in here. That's what I called this. You would do a run find, you would do a get offset and dump it into VR1. When you do that, a good way to test that your position, your reference position is good, VR offset, when you go to detail, these should all be zeros. The position found 1 is in reference to the user frame that you taught. So you're going to have some values in there because it's obvious it's not going to be at 0. That's not unrealistic. But the offset in comparison to the reference you taught, since you still haven't moved, you technically still have not moved that workpiece, it should all be 0. If you moved it 5 millimeters in your user frame of the X direction, you should be able to come in here and see that it was 5 millimeters. That calibration is really tying in your pixels per millimeter scale. That's what the calibration does. And when you do a snap and find in the programs, because you have to dump it into a VR, you can't just do it on the browser. You have to dump it into a VR. You check that VR, see that it's all zeros. Great, awesome. You're doing good. You're doing good things so far. And that's really the bulk of the work. And that's where a lot of the errors happen. Now, when I did this last week, I had some values in there, some values that were weird. And that was just because I used the 3-point method when I taught the user frame. So I'm going to come in here, I'm going to click set. There's that part that I found. It's going to give you a nice little message for the lawyers. And when I click save, okay, this is huge. You have to hit save to send it to that robot. That routine that we're referencing, that reference that we taught here, and then the vision that we're using in the teach pendant, it doesn't go to the teach pendant until you hit save. Then it's synced to the one that you're using in the browser versus the one you're using in the teach pendant code. After this video is over, we'll go over a little bit about teach pendant code. Again, I apologize again, you guys, that this video is all over the place. Okay, there's a great picture of my face. It was really tough to do this during a job. So, okay, here we got the robot. Camera's mounted. We taught our calibration's good. We taught our global positioning matching or geometric pattern matching tool. I'm going to go in here. I'm going to create a routine. I called it Vision Find Rotor. What that's going to look like is you can do it in a main routine instead of having it call this routine. But what we do is we create the routine and then we call the routine that does all of the vision work. So when we jump in here we're gonna have some comments describing what it's doing. We turn the lights on because we control it with an output. And here's our calibration check right here. We do our run find, and I'll show you what that looks like in the instructions. Instructions, next page, next page. I might have just jumped right past it. Vision. Here it is. Here's our run, find, get offset, get pass, fail, where you can be doing a histogram tool, which is kind of a different topic, but I'll explain a little bit, where this get pass, fail feature. Yikes, that is not what I wanted to happen there. This get pass, fail is getting, is it good or no good from the vision routine. So first you have to do a snap. You have to do this run, vision, find, and it would be right here is where I would have my get pass, fail. Yeah, see, I can't do it with this one because it's not it doesn't have any executional conditions tied to it, but you would find that routine, get pass, fail, and then dump it into a register. 0 is definitely not found, 1 is found, and 2 is undetermined. So basically it failed. So 1 is a pass. And then you have to have a jump label. You have to have a jump label that it's going to jump to if it fails. If you don't have a jump label, it'll fault. It'll fault every time. Here's our label, jump label 90. It jumps down here. We turn on the digital output, letting PLC know that it failed. And that's kind of how we do it, at least. So that's it, you guys. I apologize. This video kind of ran on for a little bit, but that was one of the best ways I could figure out how to teach you guys IRVision. IRVision is incredibly powerful. It's really easy to use. Once you figure it out, it's really easy to start putting it together. But if you mess up on any of the steps above it during the calibration setup, it is going to affect you down here when you're trying to move your positions. I almost forgot to show you guys a really important factor. So another big part of the whole reason that we're trying to do this is to get offsets, right, to the robot. Well, we dump these into VR1. So in a normal position register, when you make that move, you can do an offset PR. So if you want to be 100 millimeters directly above that position, you would make another PR, zero all the axes out, and then have 100 millimeters in Z. It's almost like that. It's almost identical to that, except you're offsetting by the value of the VR. So let me see if I can go find that code. Here it is. So we're moving to a pounce. We're moving to an approach, and then finally a VR1 offset. So move to PR11, 200 millimeters above the VR offset, right? Because if it's over here, if it's over here, it's over here. I want to be 200 millimeters directly above it, including that VR offset. I'm going to approach it. I'm going to get a little bit closer to it. And then finally, I'm going to go to it with no PR offset, with no Z offset, with only the VR offset. That will get me an X, Y rotation. That is everything that we want for IRVision. That's the whole point, right? We want X, we want Y, and we want rotation. Now, there are a lot of cool things you can do. Like if you do not want rotation, then you can zero it out. You can zero out that value. Yes, it may be getting rotation and dumping that into that VR, but you don't have to use a VR. You can set a PR equal to a vision register, which is what we do here. Because of reachability reasons, we had to do an offset in a different way. And here I would actually dump PR 70. I took VR1, dumped it into PR 70. I zeroed everything out but X. I wanted X. I wanted it to locate in X. Everything else, I wanted it to be 0, except for in the Y, which was kind of an approach. So you can still manipulate data of a VR. If you don't want rotate, you don't want X, you don't want Y, then dump it into a PR and then just do a PR offset. So that's a little bit about, I know I'm barely scraping the surface of IRVision. It is incredibly cool. It's pretty intuitive, and they give you these, these informations to help you understand what some of this stuff is. And then again, all these different processes they have. We usually use the GPM Locator Tool because we're just trying to find a part. We're not trying to find a blob. Sometimes we've used a blob tool. There are a lot of different tools in here. Explore around, and if you guys have any questions, feel free to reach out in the comments. I'm usually pretty good about getting back to you guys in the comments if you have questions. It may take me a couple days before I see the notifications, but I will definitely try to help you with any applications you have. I think my email is attached to my YouTube channel. So again, if you guys have any questions, feel free to email me. I appreciate you guys watching. And if you like the video, hit the like button. And if you want to keep seeing more content like this, subscribe. I think the next video we're going to be doing is going to be on palette tool. Hey guys, thanks for watching the video. If you like the content, be sure to smash that like button so I know you find this kind of content useful. Here in the future, I'm going to be posting loads of videos on Rockwell automation, PLCs, factory talk, IRVision, literally everything under the umbrella of automation. And as I learn these things, I want to share them with you. So be sure to smash that subscribe button with the notification bells on. Thank you guys again for watching, and until next time.